Good morning, everyone. Myself, Engineer Shahroz Javed, and I am working as fire safety engineer, and I have professional experience in fire alarm system design, inspection, testing, and NFPA compliance. So today we are going to cover a topic that is absolutely fundamental to fire alarm system design and honestly one that even experienced engineers sometimes get wrong in the field. So we are talking about smoke detector selection, placement and spacing as required by NFPA 72 2025 edition. So I want you to think about something for a moment. You walk into a large warehouse, a shopping mall, atrium, or a corridor with exposed ceiling beams. The question is, where exactly do you put the smoke detectors? How far apart? And does the ceiling shape matter? And does the room size matter? So the answer to all of these questions is yes. And NFPA 72 gives us very specific guidance on each one. So let's start our slides. Number one is smoke detection selection considerations, in which it reference section 17.7.4.12 and others sections. So before you can even think about placing a single detector, NFPA 72 requires you to evaluate the environment where that detector will live, and there are 9 key factors you need to consider. The number one is plume and ceiling jet flows. So when a fire starts, hot combustion gases rise as a plume and then spread horizontally as a ceiling jet. So if your detector is positioned poorly, that ceiling jet might completely miss it. And the second one is ambient temperature and humidity. A detector in a cold storage facility behaves very differently than one in a boiler room. So extreme temperatures or high humidity can cause nuisance alarms or even reduce sensitivity. And the third one is ceiling shape and surface. So is the ceiling flat and smooth? Does it have beams? Is it a waffle ceiling? Is it sloped? All of these affect how smoke travels and where the detector should go. So we will cover this in detail shortly. And the fourth one is ceiling height. This is a big one. The higher the ceiling, the longer smoke takes to reach it and the more it cools and spreads along the way. So a 10-foot ceiling and a 40-foot ceiling are completely different design problems. The fifth one is fuels and fuel configuration, and a room full of plastic storage will produce a very different fire signature than a wood frame structure. So some fuels produce fast flaming fires, others smother for a long time. And the sixth one is ventilation systems flows. HVAC systems can dilute, redirect, or even push smoke away from detectors. So in a heavily ventilated space, smoke concentration at the detector might be significantly lower than at the fire location. And the seventh one is stratification potential. It is one of the most misunderstood phenomena in fire detection, and we are going to spend real time on this in just a moment in other in our next slides. And the eighth one is installation requirements. Certain environments require uh, specific mounting methods, conduit protection, or detector types due to environmental hazards. And the ninth and the last one is detector capabilities. Not all detectors are created equal. Ionization, photoelectric, multi-criteria, spirating, and each one has strengths and weaknesses depending on the fire scenario. So the key takeaway is here is this: detector selection is not a one size fits all decision. You have to evaluate the specific environment before you pick up a detector and put it on a drive. Now moving to our below slide, which is about smoke detector design. Uh, In this slide, it tells us that in the absence of specific performance-based design criteria, detectors on ceiling up to 40 feet or 12.2 meters in height shall be placed using one of the two methods. The number one method is the distance between detectors shall not exceed a nominal spacing of 30 feet or 9.1 meters. Additionally, there must be detectors within one half the nominal spacing measured at right angles from all walls or partitions that extend upward to within the top 15% of the ceiling height. And the method 2 is all points on the ceiling must have a detector within a distance equal to or less than zero point 0.7 times the nominal 30-foot spacing, so which works out to be 21 feet or about 6.4 meters. So uh, the the zero point 0.7 multiplier comes from geometry. If you imagine a square grid of detectors spaced 30 feet apart, the farthest any ceiling point can be from a detector is the diagonal of that square, which is zero point 0.7 times 30, giving you approximately 21 feet. So method 2 is simply the geometric equivalent of method 1, just stated differently. So now we will move to our next slide, which is about stratification. So uh, the above slide shows us a diagram, and below slide shows us a real world video example which is not playable during our video presentation. So what is stratification? Here is what happens. A fire produces a hot smoke plume that rises. As that plume rises, it cools. At some point, the temperature of the rising smoke equals the temperature of the surrounding air. When that happens, the smoke stops rising. It has lost its buoyancy and it spreads horizontally at that level, forming what we call a stratification layer. So now here is the problem. If your ceiling mounted detectors are above that stratification layer and the smoke never reaches the ceiling, those detectors will never activate. So the fire could be burning below. So smoke could be filling the lower half of the building and your ceiling detectors are sitting up there completely untouched. So this is a real world failure mode. So it is not theoretical. Uh, the video, which is not playable, actually demonstrates this phenomena. So, so to overcome this, beam smoke detectors can be used to overcome the detection problem caused by a layer of hot air under the ceiling, or it can also be reduced by placing beam detectors at intermediate heights, so you can detect smoke even when stratification prevents it from reaching the ceiling. So now moving to our next slide, which is about anticipating stratification, and it is the part of the continuation of our previous slide. So these slides show us a layered approach, both in diagram form and in real building photographs. So as I discussed earlier, that we can put beam detectors at intermediate height, or can put spot type smoke detectors at intermediate height, so we can detect the smoke easily. So as above figure shown, you can notice that the top detector shown with the crossed circle is not being reached by the smoke plume. So the smoke is spreading horizontally at mid height. So the detectors at the lower levels are what will actually detect the fire. So below, as you can see in below slide, that add additional detector rows at intermediate levels. This is exactly the right approach for high ceiling spaces where stratification is anticipated. So you are placing detectors at multiple elevations to catch the smoke regardless of where it stratifies. Moving to our next slide, which is also about stratification. So as we discussed already earlier, uh, the phenomena in detail. So moving to our next slide, which is about which is basically a poll that can table 17.6.3.5.1 be used to correct smoke detector spacing for height? So the answer is false, and this surprises many people because this table is used to correct heat detector spacing for ceiling height, not smoke detectors, because for smoke detectors, height corrections are handled through performance-based design or specific provisions in section 17.7, not through that table. So this is a common mistake in the field, and it is worth remembering. So moving to our below slide, which is about spot type on smooth ceiling. So the diagram shows a room with detectors arranged on a grid. So the nominal spacing between detectors is SD equals which is 30 feet. So and wall spacing is one half of SD, that is 15 feet from all walls. So the question posed is, if SD equals 30 feet, what is the maximum radius of coverage which is R? So using method 2 from section 17.7.4.2.3.1, R equals zero point 0.7 times of 30, so giving us 21 feet, approximately 6.4 meters. So this is the baseline layout for smooth flat ceilings. Every other ceiling condition we discuss from here is the modification of this baseline in our next slides. So now let's talk about corridors. Corridors are special cases in NFP 72. They are narrow elongated spaces, and the usual area based spacing rules do not apply directly. So this slide references annex section A.17.6.3.1 bracket E. For a corridor, the detector spacing along the corridor length can be up to 30 feet. But the maximum distance from any wall in the corridor width direction is 15 feet. So if you have a corridor that is 10 feet wide, one detector can cover a 30-foot run of that corridor because the walls on either side are only 5 feet away, well within the 15-foot maximum. And our below slide, it is simply asking the question that what is the allowable design spacing for a 30-foot nominal detector spacing. So the answer using the zero point 0.7 rule is 21 feet as the coverage radius. Moving to our next slide, which is about uh, corridors spacing. So this slide gives us a worked example with a 20-foot nominal spacing corridor scenario. In this scenario, zero point 0.7 times of 20 gives us 14 feet maximum coverage radius, approximately 4.3 meters. So and along the corridor length, detectors are spaced at 40 feet because that is the diagonal distance between managed within the corridor geometry. So the practical message here is simple. Corridors require their own spacing analysis. Do not just apply open area rules to corridor conditions. Below side tells us about joists and beams, which is the most technically detailed parts of smoke detector design. So NFPA 72 distinguishes three conditions based on beam depth relative to ceiling height. The condition number one is if beam depth less than 10% of ceiling height. So if the beams are shallow relative to the ceiling and are less than 10% of the height, which is H, they are considered insignificant obstacles. In this case, you simply use smooth ceiling spacing. The beams do not require any modification to your design. Moving to our second slide and second condition, if beam depth is 10% or more of ceiling height and beams are spaced zero point 0.4 H or more apart. So in this case, when beams are deep and widely spaced, each bay between beams act like a separate room. So the rule is one detector per pocket, meaning one detector must be placed in each bay between beams. So the detectors sit in each compartment created by the deep beams. Okay, now we will move to our next slide and condition number 3. Uh, if beam depth is 10% or more of ceiling height and beams are spaced less than 0.4 h apart. When beams are deep but closely spaced, the spacing perpendicular to the deep beams must be reduced to one half the smooth ceiling spacing. So instead of 30 feet, your cross beam spacing becomes 15 feet. So along the beam direction, you still use standard smooth ceiling spacing. And now moving to our below slide, which is about waffle ceilings. A waffle ceiling has beams running in both directions, forming a grid of pockets. NFPA requires you to treat each direction separately, evaluate the beam depth and spacing in each direction independently, and apply the appropriate reduction. So the result is that waffle ceilings often require significantly denser detector placement than smooth ceiling. The grid of deep pockets means smoke is compartmentalized in two dimensions simultaneously. Moving to our last slide, which is about corridors with beams and joist. So for these narrow corridors with width, you use smooth ceiling spacing along the corridor length. The logic is here that the narrow corridor width already constrains smoke movement, and the beam related reductions are not necessary in the same as for wide open spaces. Finally, our last slide covers small rooms with joists or beams. So the rule here is straightforward. If the room is less than 900 square feet or 84 square meters, use smooth ceiling spacing regardless of beam conditions. So the reasoning is practical. In a small room, smoke fills the space quickly. So the beam compartmentalization effect that matters in large spaces is not significant when the entire room volume is limited. So one well-placed detector will cover the room regardless of beam depth or spacing. So this is all from my side, and thank you so much for your attention and keen listening, and hope you all are have understand the concepts which I have shared with you. So thank you so much.